One of the things we may not think about very much is that the direct control of machinery by the power of our mind is already here. And this is a monkey that's been trained to use that robotic arm in order to feed itself. It has electrodes implanted into its brain, and it uses those brain signals to train the arm in order to reach for food and give the food to the monkey. There are also similar experiments using pigs. Now, the implications of this are far-reaching. One obvious thing is that anybody who suffers from a severe disability is now able to type or move or talk to their families using this direct mind control.
So electronic components fall into two categories. That is the passive component and the active component. Now, passive components are things like resistors, capacitors and inductors, and active components are things like diodes and transistors. The first transistor ever invented that we would recognize as a transistor was in 1947 at Bell Labs. But of course, a transistor came out of something and it was performing an action to solve a problem. A transistor can do one of two things. It can either switch or it can amplify. Both of them very key to what we do in electronics, because you can use these components to make stuff. The main thing that you can actually make with them is control. You control a signal. So it takes some kind of electromechanical input, like say a microphone, directs it, and it will output it in another electromechanical system, like a loudspeaker. And of course we can swap loudspeakers and we can make it a greater volume, so you whisper in the microphone and shout out of the speaker. And there's things you can do with it when you route it through as a signal or change the power level to make an input perform an action as an output. So really electronics is all about control. And of course, control is important to us. We really want to control stuff. That's why Alexa is so important, because you can sit on your sofa and say, Alexa, turn up the television. And it will control the television with you doing nothing. And of course, that's really, really exciting. But the functions of switching and amplification that a transistor does were done before in a mechanical or electromechanical way. That's where Colossus came from. Colossus, as the Bletchley Park computer, was basically a lot of electromechanical switches. It wasn't until something like ENIAC, which was the US Navy computer, that used valves for those functions that we began to see the electronics coming in. And of course, when transistors were developed, they allowed Moore's law to take hold of everybody's mind, shrinking it down, making it more powerful, making it tinier and tinier and tinier. And of course, now we've got millions of transistors on a chip that can do some amazing things, and it looks almost as if the computer can think. But of course, the computer can't think, it can only switch. Now, switching is something that can be done with something like a relay in an electromechanical way. Amplification can use something like a magnetic amplifier, which uses core saturation of a transformer to amplify the current. And these kind of devices were very stable, and opposed to vacuum tubes at the time, they were better suited for things like torpedo control, where it was a rugged environment and a tube just wouldn't last. Now, as we go further and further with transistors, trying to get them to do more and more, we're still very interested in that aspect of control. We would think, when looking at transistors, that we were getting to where we needed to be with only really the questions of how to make it smaller. But there is a whole other issue here, and that issue is the one I keep hinting at: control. How is it, or how could we get a direct transition between a brain and a computer? That interface between the organic and the silicon, how are we going to actually do that? Well, there's a lot of research, particularly in the last 10 years on this, and they've taken a step back. And it's one of those things where you take a step back to take a step forward. If you take a step back and look at the basic function of a transistor, particularly its switching function, how could you manage that so that you could directly connect it to a neuron and get the neuron to switch that transistor? Now, there have been efforts to make that silicon organic interface directly with a silicon-based transistor, and they're not very successful. Some things have been introduced with graphene, and that is very current, but a really interesting one is a liquid transistor. Now, a silicon transistor works because we have two different types of semiconductor. It's either NPN or PNP. and we have a junction or a connection to each of those. If we actually put a voltage down one of them, we can control the flow of the voltage, whether it goes one route or it goes the other route, and that is what a switch is. Equally, if we put a voltage down one, we can change the level of voltage flowing through, and that's what the amplifier is. So these two components as three sections with that ability to do that is what a transistor is, and we can replicate that using liquid, and here's an example of one. We have a conductive material joined by a channel. Above that channel is an electrolyte. If we put a current down, we'll change the ion concentration in that electrolyte, which will affect the channel. As that ion concentration changes and affects the channel, the conductivity of the channel will change, and so we can amplify or switch, so we can make it non-conductive or conductive through that channel by changing the ion concentration in the electrolyte, which we can do by an electrical signal just above. Now, this has been researched since about 1953, actually, all the way through. And because the liquid is a much more forgiving environment for interfacing to the organic. So we can stick a brain cell into that liquid and it will quite happily live as long as we get that liquid right. And of course, it's going to be affected by the ion concentration in the liquid. That's going to affect the cell membrane. So the cell membrane, and therefore the brain, is going to be able to read the state of that switch at any particular time. So the effort now is to grow the brain cell axon into that channel where we can affect the electrolyte concentration. And of course, that means that the brain can interface directly with the computer. And in terms of controlling it, we won't even need to speak. We can just lay like blobs on our sofa and think, Alexa, change the channel. I mean, that's a bit of a joke. Obviously, what they're really interested in, and a lot of this research is being done by the Defence Department, what they're really interested in is fast control of things like tanks and aeroplanes, and drone control, and remote controls. You have a soldier sitting safely, and his remote control drone is on the battlefield fighting. So a lot of this has been done by various defence departments to integrate the soldier with the machinery, so there is direct thought control. Now, that is, well, two things for me. One, it's kind of exciting. Two, it's kind of worrying. But that does seem to be where we're going, and stepping back to build those much larger liquid transistors, because these things are about this big at the moment, stepping back to build those has proven very fruitful for that move forward into mind control of machine. Anyway, I thought I would share that with you. I hope it was of interest. Thank you very much for watching, and please do remember to like and subscribe.